Okay, so your test is going to be on 1.1, 1.2, and 1.4. I'm going to go through 1.1 pretty quickly because I feel like we've done this 100 times. So the parent function of a graph that's linear just goes through the origin like this. And then plus 3 means that we go up 3. So our graph just gets shifted up 3 places. For number 2, we have an absolute value graph. The minus 1 means that we go down 1. So our graph just shifts down, and we go from there. Number 3, this 1/2 means that we have a vertical compression or vertical shrink. So this would be a quadratic graph, and a compression means that we make it chunkier. We squish it down vertically. So we're making our graph fatter. So it's going to look like that. Number 4, we have h of x is equal to 4. This is a constant graph. Our constant goes through f of x is equal to 1. So f of x is equal to 4, or h of x is equal to 4. We just shift it up 3 units. So even though it says 4, we're only going up 3. Just because our parent starts at 1 already, so then we just shift it up 3 places to get to 4. For 5, we have a reflection on the x-axis. Since it's outside, it's a reflection on the x, and we shift down 3. So our parent graph would look like this. Our reflection just flips it upside down, and we shift it down 3. So our new graph would look like that. And then lastly, for number 6, the negative means that it is a reflection on the x. The 3 means that it is a vertical stretch. And then this plus 3 inside means that we are going to the left 3. So we need to take our quadratic graph. We flip it upside down. We move to the left 3. And then we have a vertical stretch. So we're going to make it skinnier. Any questions on 1 through 6? So you guys should know by now, we've had so much practice doing this, how to go from our equation to our graph, and also how to go from the graph. If it gives you this graph, you need to know that your equation looks like this. All right, let's go to number 7. So here we're going to take our f of x and apply our transformations to get g of x. So we have a reflection in the x-axis, means that we are multiplying the outside by a negative, and a translation 4 units to the left means that we add 4 on the inside. So our g of x, since we have an absolute value graph to start, we just put our negative outside the absolute value and our plus 4 inside the absolute value. For the next one, we have a vertical shrink by a factor of 1/2. So that means we are multiplying the outside by 1/2. And then a translation 2 units up would be we add 2 to the outside. So our g of x, again we have an absolute value, so we just put 1/2 outside our absolute value and plus 2 outside. For number 9, we have a translation 3 units down, which would be x minus 3 on the outside and a reflection in the y-axis, so we multiply the inside by a negative x. So our g of x graph, we're just applying these to our x. So we have a negative on the inside and a minus 3 on the outside. We don't need our parentheses here, so we could just make this negative x minus 3. The last class asked, how can we tell now if this is a reflection on the y-axis or a reflection on the x-axis? If we have a graph here, our parent function of x would go right through the middle here. And this graph, if we said that this was a reflection on the y-axis, we flip it with respect to the y-axis, so now it looks like this, and then we just shift it down 3. So it would now look like this one. If we had a reflection on the x-axis, we would flip it on the x-axis, so it would look like this. And we shift it down 3, so it would be here. Oh, sorry guys. So whether this is inside or outside, it doesn't matter. When it's linear, we don't need the parentheses because we end up with the same thing. So a reflection on the y-axis here or the x-axis would look the same, so that's why we can just get rid of our parentheses.
On the test, let's say we do put the parentheses, would that be wrong? Or?
No,
Okay.
But just know if it's multiple choice, you would see your answer like this one.
Okay.
Any questions from the first page? All right, I'm gonna do 12 and 14, and I'll show you guys the answers for 13. 13, we just got some absurd fractions, so on the test, I'll try to get you guys some good numbers, some good even whole numbers, because 13 was just a pain to do. So first thing I wanna do here is get this x is equal to 4z in the proper order. So I want our x to come first. We don't have a y. I'm going to move the 4z over to the other side by subtracting 4z from both sides. And then I'm just left with 0 on the other side of our equal sign. So I just want to get this into the right order. Since our y, we don't have a y in this equation, what I want to do is combine the first two to get rid of our y, so then I can combine that new equation with this third equation. So in order to get rid of our y's by combining the first two equations, I need to multiply the first one by -3. So our new first equation is going to be -3x minus 3y minus 3z is equal to -9. And now I can add these two together. So -3x minus x would be -4x. Our y's cancel out. -3z plus 2z is minus z. And -9 minus 8 is -17. So now I have two equations with two variables. So now I need to combine these two equations and get one of our variables to cancel out. So what I'm going to do is multiply the first equation by 4, because that'll give us a positive 4x and a negative 4x, then our x's will cancel out. So our new black equation here would be 4x minus 16z is equal to 0. And then I'm going to add these two together. Our x's cancel out. -z minus 16z is -17z. And that's equal to -17z. And then I can just divide both sides by -17. So z is equal to 1. Now I can take this and plug it into one of our equations that only have two variables. So I'm going to plug it into the first one up here. So I have x minus 4 times 1 is equal to 0. X minus 4 equals 0. So x is equal to 4. Now that I have two variables, I can plug it into one of our equations with three variables to find out what y is. So I'm going to plug it into the first one up here. So I have 4 plus y plus 1 is equal to 3. Y plus 5 is equal to 3. Subtract 5 on both sides, so y is equal to negative 2. Now I can rewrite this as our coordinate point. Remember, we just go x, y, z. So 4, negative 2, 1. All right, let's take a look at 14. So for this one, I'm going to get our z's to cancel out. So first thing I'm going to do is multiply one of the first two equations by a negative. So I'm just going to do the top one and combine it with the second equation. So I have a negative x minus y minus z is equal to negative 2. And now I can add these two equations together. So I get negative 3x minus 4, oh no, this would be negative x plus 2x is just x. Then this is minus 4y. Our z's cancel out, and it's equal to 9. Now I'm going to multiply our second equation by 2 and combine it with the third. Again, to cancel out our z's, because we have to keep, if we canceled out our z's to start, we have to cancel out our z's again. So we have 4x when we multiply it by 2 minus 6y plus 2z is equal to 22. And now we add this with our third equation. So 4x minus 3x is just x. Negative 6y plus 2y is negative 4y. And then our z's cancel out. 22 minus 13 is 9. Now when we multiply one of these equations by a negative number to get our x's to cancel out, so we have negative x plus 4y minus 9, and we combine them, we get 0 is equal to 0. I don't remember if I mentioned this yesterday, but I know when we did the notes, I called this all solutions, but I think the book calls it infinitely many solutions. So if there is one like this on the test, just know that infinitely many solutions is the same thing as all solutions. So you can either have one solution, infinitely many solutions, or no solution. All right, any questions on these? Again, the answer for 13, it's posted on Canvas. I posted all the answers to this on Canvas. I don't want to work it out right now because it'll just take way too long, and it's all three, x, y, and z are fractions. So, all right, let's take a look at 15, 16, and 17. For these three, we need to match the transformation of f of x is equal to x with its graph, then write a rule for g. A lot of people put, I don't know what you guys did for these, but just think of this f of x is x. It tells us f of x is equal to x, so we can just change out this f of x with x. This plus 3 tells us we're going up 3. This 2 tells us that it is a vertical stretch. So looking at our graphs, which one goes up 3 and has a vertical stretch, A, B, or C? B. Awesome. So 15, the answer is B. Now for 16, we have this -2, so this tells us it's going down 2. And then the 3 tells us that we have a vertical stretch again. So which one goes down 2 and has a vertical stretch?
C.
C. Awesome. And then we know the third one's going to be A, but let's just check to make sure we did it all right. So we're going down 3. And we have a vertical stretch. And this negative means that we have a reflection on the x-axis. So the only graph that all 3 of these apply to would be A. So we can see here that our normal graph would go through here, but now we are shifting it down 3. So since this graph starts here, it's the only one that goes down 3. Any questions from these 3? Okay, number 18. So here we need to describe the transformation of the graph of f of x is equal to 2x minus 4. So we're going from f of x to this g graph. So the first thing I want to do is graph this f of x and see what it looks like compared to g. So I'm going to plug in values for x, get some values for y, and plot those points. What's a number I can plug in for x? Awesome. 1, 0, and -1. We could plug in anything. We could plug in 2, 4, doesn't matter. We can plug in anything, just as long as we have a variety. So when we plug in 1, we have 2 times 1 minus 4, which would be -2. So our point here would be 0, would be 1, -2. So we go to the right 1 and down 2. When we plug in 0, we get 0 minus 4, which is -4. So our next point is 0, -4. So we stay on 0, go down 4, and then we plug in. If I plug in -1, it's going to be off of our graph. So I definitely could if I was drawing my own graph, but I kind of want to get one from this side of our graph. So I'm going to plug in 3. Again, it doesn't matter. I just want a variety of points. And I just can see that -1 is going to be over here, and I don't want it to be off of our graph. So by plugging in 3, we get 2 times 3 minus 4. So 6 minus 4 is 2. So when I plug in 3, I get 2. Now I can connect these 3 dots with the line. So I see that the new green line that I have, or not even new, this is our f of x. Our f of x line has the same slope as our g graph. We just shift it. So looking at our graph, we're taking f of x, so this 2x minus 4, and to get to g, we can shift it to the left 2. A shift to the left 2 means that we are adding 2 on the inside, and then we're shifting it up 1 to get to here. So this means that we are adding 1 on the outside. So now we need to take these 2 transformations and put them into our f of x graph, our f of x function. So we have 2. We plug in what's in our parentheses in for x. So 2 times x plus 2, and then minus 4 plus 1. I can simplify this a bit. So I have 2 times x plus 2 Negative 4 plus 1 would be minus 3. So our g of x would be 2 times x plus 2 minus 3, which if we look at our graph, we have a vertical stretch. We have a shift to the left 2, so we're going left 2, and then we're going down 3. So going down 3 from here would put our graph there, and then we have a line right through there. So perfect. We could leave it like this, or you could multiply the 2 out. So if you wanted to, we could multiply and distribute that 2. So 2x plus 4 minus 3. This would be 2x plus 4 minus 3 would be plus 1. So looking at this graph here, we have a vertical stretch, and we shift it up 1, so we just shift it up from our origin 1, which would be the same exact line. So we could write it like this, or we could write it like this. They're the same exact line, doesn't matter. Any questions?